Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Chapter 6, Integration and Accumulation of Change. Today's topic is 6.4, which is the fundamental theorem of calculus and accumulation functions. Enjoy today's notes.
Welcome to 6.4 Accumulation Functions. In lessons 6.2 and 6.3, we learned about the idea of Riemann sums, which is the idea of using rectangles, whether they are left, right, or middle, in order to approximate the area under the curve. We also learned about this idea of trapezoids being able to be drawn under the curve, these vertical trapezoids, to give us a more accurate area. In general, though, we also recognize in that 6.2 lesson that the more rectangles, or I guess trapezoids, that you have, the more accurate an estimate would be. So if you're trying to find that exact area under the curve, the more rectangles you have, the thinner those rectangles are, the closer to the actual value you will have. Now, if I have some arbitrary graph, let's just draw this function, and we'll say we've got this function, say, going from x equals a to x equals b, and I want to say represent the area, the exact area under the curve between the curve and the x-axis from a to b. We're going to introduce this new piece of vocabulary, which is what's called an integral. So an integral, which is going to be a huge, huge thing in this chapter and moving forward, this idea of what an integral is. What is an integral? Well, first off, let's show how we write it. So we have this sort of S-shaped thing, and I'll put an a on the top, I'll put a b on the bottom. We'll say that this is our function f of x, so we're going to say that this is f of x dx. What this is this represents, this symbol and this sort of mathematical statement represents the exact area. It's the exact area under the curve. And remember, we talked about in one of our previous videos that the phrase under the curve means between the curve and the x-axis. So it represents the exact area under the curve of f of x from x equals a to x equals b. So an integral represents the exact area under the curve of f of x from x equals a to x equals b. Let's break down, though, what we see in this integral. So we have this this sort of new way to write this area. First off, let's start with this S-shaped thing. This is referred to as the integral symbol. It's the integral symbol. This f of x here is the function that is being integrated. It's called the integrand. So the integrand, aka the function being integrated. And that's just this part right here. Our x equals a and our x equals b are referred to as the limits of integration. They're essentially telling you in this case what x values you're finding the integral of, what x values you're finding the area beneath the curve, under the curve, the lower limit of integration and the upper limit of integration is what they're referred to. And then finally, this part here on the end, this dx. This is very similar to we might remember back when we're doing derivatives, that we've got this like dy dx. And so what does the dx mean in this case? We're saying here, for this dy dx, that we're taking the derivative of y with respect to the variable x. So we're taking the derivative of the function y with respect to the variable x. In this context, this dx functions the same way. We're saying we're taking the integral of this function f of x with respect to the variable of x. So it's identifying the main variable that we're using for integration. Great. With that introduction, we're going to get into the actual content for 6.4. So let's do that. We now know what an integral is, what that symbol is, and we'll see some examples with it and try to see that going forward. All right, so on to the notes from 6.4. The last lesson we learned about this thing that's called the definite integral, where we said the integral from a to b of f of x dx represents the area under the curve of f of x on the interval from x equals a to x equals b, or the interval from a to b. Specifically here, I'd notice we're seeing this word definite here for the first time. This word definite integral is a type of integral where they give you limits of integration. So limits of integration. And when I say limits of integration, I'm saying specifically that there is some x equals a and x equals b where this integral is, we're finding the area of the curve between those two x values. Sometimes later on in this chapter and going forward, we're going to see integrals that don't have limits of integration, and those are what are called indefinite integrals. And so we're being very specific today in talking about these definite integrals going from x equals a to x equals b. Again, this representing the area under the curve of f of x between x equals a and x equals b. Now, for today, let us say that we know the interval starts at a, but we don't know where it stops. So for example, maybe we have some sort of function, and here's our our function looking like this, and we have an a value, and we know that we're finding the area under the curve of this part, and we know that it's starting at x equals a, but we don't know where x is. Maybe x is here, maybe x is somewhere to the left, maybe x is somewhere to the right, but in general, that would give us some interval, and that interval would be between a and some x value that we don't know, right? This x could be moving to the right, it could be moving to the left, where a is a constant and x is some unknown variable. We can represent that as a new function that looks like this. Well, I'm going to call this, we'll say that this is the integral from a, right? A is where this is the x value where this we're starting to take the area, and it's going to go all the way up to wherever x is. So x is going to be at the top. It's going to be our upper limit of integration. Our function here, I'm going to actually, the variables here are going to be slightly different. We're going to then have an f of t dt. So we can represent that as a new function that looks like this. This capital F of x is equal to the integral from a to x of lowercase f of t dt. We are being very specific in having a capital F versus a lowercase f. They mean different things, and we'll learn more about how they are different later in this chapter. But for now, we just need to make sure that, and to point out that they are different from each other. Okay, great. So we also, again, I want to just remind you that we don't know, that x is unknown in this case. And so let's talk about what this is then. So we have some sort of function, and we're finding the area between a and some x value that we've got. And, in general, we're accumulating the area, right? We're still doing these like accumulation functions. So let's see how this looks in number one. Let f of x be equal to the integral from 0 to x of f of t dt. Use the graph of f in the figure to find the values of the table on the interval from 0 to 5. Complete the table. So if x is 0, we are finding the integral from 0 to 0 of f of t dt. This over here is our function f of t. And so if I'm starting at 0, so x equals 0, I'm drawing my vertical line to show where this area is going to start, and it stops at the exact same x value, there's really no opportunity for any area to have accumulated. So because of that, when these limits of integration are the same, no area could have accumulated, so that is going to be equal to 0 here. Okay, well, what happens if we do the integral from 0 to 1 of f of t dt? Now, we visually recognize that means that we're finding the area between 0, which we've already got highlighted with this vertical line, up to x equals 1. And we're essentially finding the area of this shape, which we've got right here, and it looks like a trapezoid to me. We could either, find the area of the trapezoid, or we can maybe count the boxes. But in this case, we've got, 1, 2, and then 2.5 for the area of that trapezoid. Okay, well, what happens now if x is 2? So 2 would be going to the top limit of integration here. So we'd be doing 0 to 2 of f of t dt. And so we're no longer stopping at this vertical line that we've got here, but in fact, we're going all the way to x equals 2, which is right here. And we're now finding this area of this box. So we've already accumulated the area from, this 2.5, but now it looks like we're adding another half in here and another 1 here. So that looks like we're now at 4. There's 4 total units of area between x equals 0 and x equals 2. What happens if we go to 3? Okay, well, now our limits of integration are going from 0 to 3 of f of t dt. Well, we're going to get rid of this. We're not going to stop at 2 anymore. We're going to go all the way up to 3, which is right here. And so now we're finding all of this area, and so we're adding an extra unit of area there. So that's going to bring us up to 5 total units of area. What about 4? Okay, well, that's going to be from 0 to 4 of f of t dt. And that's going to have us add in this little triangle right here, which has half a unit of area. So that brings us to 5.5. And then if we go all the way to x equals 5 right here, that's going to be the integral from 0 to 5 of f of t dt. That's the area under the curve of f of t between x equals 0 and x equals 5. So we have all of this area we've done all the way up to 4. Now we've got this here bring us to 5, which is right here. And this is also a half a unit, but it's it's below the x-axis. So it's actually negative area since it's below the x-axis. And so that's going to actually subtract a half unit of area away from us and bring us back to 5. We were at 5.5 at 4, and then we lost a half a unit of area because we went below the x-axis. So that gave us 5 total units of area. This idea of what we just did, where we're essentially this x value is changing and we're finding more area as it goes on, is what's called an accumulation function. It's called an accumulation function. We are accumulating the area as that x value increases. We're getting more and more and more area. And we're paying attention, obviously, to whether that area is positive or negative, because it's going to either increase the total amount of area or subtract that amount of area. Now, this brings us to one of the most important things in this class, which is called the fundamental theorem of calculus. It's such a powerful name. It's the fundamental theorem of calculus. Interestingly enough, there are 2 parts to it. And depending upon the textbook that you and your class use, you might do one or the other first. This is generally referred to, by me as the second one. But we're doing it in this order because of the way the AP Calculus, the new CED, is sort of suggesting us to go in this particular route. It really doesn't matter which way you do it, but this is often referred to as the second part of the fundamental theorem of calculus, and we'll have to find out what the first part is later in this chapter. But what does it say? It says, if a is a constant and f is a continuous function, then, whoa, what is this? Well, so this is d dx, so the derivative of this integral, of this accumulation function. So we recognize this part here as the accumulation function, which we were just sort of working with up here, right? It's called an accumulation function. And then we recognize this part from all of our work from chapter, 2 through 5, that this is saying, hey, take the derivative of it. So if we take the derivative of an integral, what do we get? So we're taking the derivative of this thing that is the area. Interestingly enough, it actually is going to give us just f of x, lowercase f of x. What essentially happens is that the derivative and the integral canceled each other out. And I took that upper limit of integration and plugged that in for my t here. So this upper limit of integration, when I took that derivative of that integral, became the input for my function, and then the derivative and integral canceled each other out. What? That's crazy. So what does this tell us then? Well, if they cancel each other out, then the derivatives and integrals have to be inverses of each other, right? Just like multiplication and division cancel each other out, just like addition and subtraction cancel each other out, just like square roots and squareds cancel each other out, an integral and a derivative cancel each other out because they are inverses. In example 1, the graph of f is the derivative of capital F of x. So notice here, the graph of this lowercase of f is the derivative of this capital f of x. So f of x, this capital F of x, is what's called antiderivative of f of x. So an interesting result of that, thinking back to what we know from earlier in this year, we know obviously like lowercase f of x, if you take the derivative of it, right, and we say the derivative of it, that we get f prime of x, and if we take the derivative of that, we get f double prime of x. But what we can do then is we can actually go in the opposite direction to have this thing that's called an antiderivative, which we now then call capital F of x. So an interesting result of that is that, capital F of x is the antiderivative of f of x, but this relationship also works in the opposite direction. If I take the derivative of capital F of x, I will have lowercase f of x. Interesting. All right, so and there's some common variations of the FTC, specifically where like normally the fundamental theorem of calculus, we've got like a constant down in the lower limit of integration, and we have a variable in the upper limit of integration. The variations of the FTC are where we suddenly have functions in the upper or lower limits of integration. And ultimately what happens when you have a function inside of this like derivative and integration function is we're going to end up using the chain rule. These variations of the FTC are all about the chain rule from way back when, earlier this year. But how does it work? Well, we see, the derivative and the integral here. We see that they're going to cancel each other out. And just like what we said earlier, that upper limit of integration is going to go in to become the input of our function. So this is going to become f of g of x. But because we're taking the derivative here, when we do that, we're going to end up needing to take the derivative of the inside function, multiplying by the derivative of the inside function, and we do in fact end up with g prime of x. So the derivative of the integral from x equals a to x equals g of x of f of t dt is f of g of x times g prime of x, which is in fact the chain rule. That is exactly what the chain rule is. That's super cool. But what happens then if we have a function in the upper limit of integration and in the lower limit of integration? Well, this is actually sort of like a double chain rule one. We're going to plug in g of x first and have sort of the same expression that we just had. So this is f of g of x times the derivative of the inside, so times g prime of x. But then we're going to subtract the same idea with this h of x. We're going to plug h of x into this function and apply the chain rule for it. So that's going to be f of h of x times the derivative of the inside, h prime of x. Now, we'll talk later about why we're subtracting here, later in this chapter when we get more into how we can evaluate integrals using equations. But for right now, it's enough to know that if you have a function in the upper limit and lower limit of integration, that it's going to be using this sort of like double chain rule format. It did the chain rule first, it subtracted, it did the chain rule twice. Let's see this in some problems. So here, all of these look like we're taking, we have f of x, capital F of x, and they're asking us to take the derivative, right? Capital F prime of x, the derivative of f of x. So we're going to be applying our fundamental theorem of calculus in these different ways. So in this case, we notice that our upper limit of integration is x here. In that case, it's pretty straightforward. No chain rule or anything like that is needed because it's just the variable. We're going to end up plugging the x in for both of the t's here. And so capital F prime of x is going to be equal to 3x squared plus 4x. And that's actually it. When you have just an x up in that upper limit of integration, that is pretty nice. It's pretty nice that you can just do that. Cool. So that's the base example. We'll take a look at 2 and 3, where we notice now in 2 and 3, we have these upper limits of integration that are functions. So in this case, because it's more complicated than x, we're going to be using these these variations of the FTC that we talked about here, where we need to apply the chain rule. And so in this case, the derivative of capital F of x, we'll put capital F prime of x, is going to be equal to sine of x cubed. That x cubed went in for the t. But then, of course, because we're applying the chain rule, we need to multiply by the derivative of the inside. That's going to be 3x squared. So we could write this in general, 3x squared times sine of x cubed. That is how I would write that one. For this one, same idea. Capital F prime of x is going to be equal to h of 4x times, so in this case, like, we actually don't have a specific function here, but we're plugging that 4x in for the t, and then we need to multiply by the derivative of the inside, so the derivative of 4x is 4. So altogether, that's going to equal 4h of 4x. That is what the derivative would be. For our two, number 4 and 5 here, these look like the final ones, we see upper limits of integration and lower limits of integration that are not constants. Even though this is an x up here, the original fundamental theorem of calculus, you'll notice that they said a is a constant. That lower limit of integration is a constant. And so the original base form of this is only when the lower limit is a constant. And so since even though it's just an x up there, the lower limit here is a variable and not a constant, so we need to apply that variation here. So what do? The derivative of capital F of x we'll call capital F prime of x, and that's going to equal 5. And instead of the t, we're going to replace the x in. But we also need to multiply by the derivative of the inside. The derivative of x is just 1. So I'm going to leave that there. We're going to subtract, because of that variant, we subtract, notice, the two parts. And then we're going to say 5 times negative x. That negative x is now going in for our t. And we're going to multiply by the derivative of negative x, which is negative 1. So this looks like this is going to be equal to 5x, and then we have negative 5 times x times negative x times negative 1. Those negatives cancel, so this is going to be 5x minus 5x. This is going to be equal to 0 for this particular one. So the derivative of this function from negative x to x, the derivative of the integral from negative x to x is going to be equal to 0. Last one, number 5. The derivative here is going to be equal to what looks like 3x quantity squared minus 3x. So we substitute that 3x in for both of these t's, and then we need to multiply by the derivative of 3x. So we're going to multiply by 3. And then we're going to subtract. So we're going to subtract here the same thing, except we're plugging in 2x's in for both of those. So 2x quantity squared minus 2x times the derivative of 2x, which is 2. So if we try to simplify, let's see what we've got. So we've got, 9x squared minus 3x times 3 minus 4x squared minus 2x times 2. And so that's going to be equal to 27x squared minus 9x minus 8x squared plus 4x. Got to be careful here. We've got a subtraction and a subtraction, so that's why we're adding right here. And then we're going to combine our like terms. So we've got 19x squared, and then minus 5x. So that is what our derivative capital F prime of x would be equal to. Would be equal to that function right there. But that's it for our notes for today. As usual, we've got practice. Check those out. Try some of these. Check your answers with the posted solutions. Please come to class with any questions that you've got, and good luck on your mastery check. Have a great day.